Hello, everyone. Welcome to the ASA section on Teaching Statistics in the Health Sciences, or TSHS, the Fall 2024 webinar. My name is Melinda Higgins. I'm the current chair for this section, and we're a section within the American Statistics Association that's devoted to excellence in teaching statistics and conducting statistics education research in the health sciences. And our goal is to promote communication around these activities, professionals that are interested in teaching statistics. And if you want to learn more about our section, I encourage you to visit the links shown here for like our website and our blog. And we post things about various section activities like these webinars. We also do resource reviews and member highlights. We also have many resources for statistical educators. For example, if you're looking for real world data sets to use in teaching, I encourage you to join our section and check out the resources portal, where we have lots of data sets that are free for section members to use. And so for today's webinar, we're happy to introduce Hilary Watt of the Imperial College of London. Hilary indulges her passion of finding innovative ways to teach statistics. She focuses on clarity of language and image-based explanation. She trials them with her students to find strategies that appear to work, with further insights into language that was gained from survey of medical statistics educators, finding language that they use to interpret p-values and confidence intervals. She prepares resources that help students efficiently prepare data for analysis, and she is a statistical co-applicant on many funded randomized control trials and fellowship applications. And today, Hilary is going to be presenting her talk on clarifying practical relevance of p-values and confidence intervals, with clear choices of words and images that foster conceptual understanding and steer away from common misconceptions. And for the audience information today, our webinar is being recorded and will be posted on the TSHS website after the session, and these videos can be viewed on our YouTube website. So without further ado, I will hand you off to Hilary.
Thank you very much, Melinda. Okay, so I'm talking about steering away from major misconceptions, and I'm including within that concerns over poor standards. I guess a lot of you are aware the ASA and Ron Wasserstein and many other people have been doing their best to find strategies to improve standards of interpretation in the applied literature, in health sciences and many other areas as well. The concern is primarily division of results, primarily according to whether p is less than 0.05. So that's the biggest concern. And the issues that can follow on from that, half of research articles say they found no association based purely on p greater than 0.05. And some go further to imply that p greater than 0.05 proves no association. No doubt people are aware if you get a very narrow confidence interval around the null effect, then that could be legitimate. But people are very often saying that when they've got broad confidence intervals with clinically relevant values within the confidence intervals. No doubt I've done that. It's so widespread. I'm sure a lot of people will have called that no association. And it does take quite a concerted effort to go against what is quite common practice. The opposite issue, of course, now we've got loads of really big data sets, and so people might imply they've got important associations solely because p is less than 0.05. And with huge data sets, there might be very weak associations that are clinically irrelevant. There's an encouragement to focus more on confidence intervals, but it's not good if you interpret confidence intervals according to whether they imply p is less than 0.05, then you obviously fall into all the same issues. Biggest misconception with confidence intervals is that they contain 95% of the observations. A major misconception, which in my experience is relatively common, or not uncommon anyway. So good practice, focusing more on estimation with confidence intervals or credibility intervals or something similar. And so we should look at the clinical relevance of the calculated results and each end of the confidence intervals. And if we're also looking at p-values, this talk is about p-values as well, then they should be in a more supporting role to the strengths of association, and we should interpret them on a continuous scale. There's an article by Amrine in Nature that you may be aware of, summarizing these issues. Does it matter? I'm looking at a historic example here, streptokinase for myocardial infarction. So does this reduce risk of heart attack or risk of death in people that are having a heart attack? So it should be administered as quickly as possible when they start having their heart attack. There's studies conducted, 59 is the earliest, a lot of studies in 1970s, and then a few in the 80s. Up to and including the 70s, the majority of studies find p greater than 0.05. 79%. If we interpret that as no difference, then it looks like that's quite robust evidence for no difference. Streptokinase doesn't help. It doesn't reduce mortality. That's what you'd conclude from that. On the other hand, you can vote count how many odds ratios are less than 1. So the direction of effect suggests that streptokinase is protective rather than having odds ratios greater than 1, which suggests that streptokinase is harmful and increases the risk of death. And then there's some weak suggestion, 63% of studies have got odds ratios less than 1, a weak suggestion that maybe streptokinase may be associated with reduction in death. But it's pretty weak evidence based on a lot of studies. Each individual study is underpowered. This way of summarizing the data is then also very underpowered. Meta-analysis obviously is a much better way of doing it, and the meta-analysis of the results, even if you only include studies up to the end of the 70s, that gives a narrow confidence interval, which is a certain distance away from 1. Very strong evidence that streptokinase does reduce deaths from heart attack. As I say, this is a historical example. They didn't do many meta-analysis at the time. It wasn't really respected. All these studies hadn't changed clinical practice, and streptokinase wasn't much used. And they decided they needed an absolutely huge study to change clinical practice. And they needed a very, very tiny p-value. So they powered the study to find a very, very narrow confidence interval. And they did indeed find very, very strong evidence from one single result that streptokinase was indeed, it did reduce death rate in people having heart attack. Story is one reason why we now do more meta-analysis. And it probably wouldn't be considered ethical to power a study to find such a very, very tiny p-value these days. And we would consider changing clinical practice on the results of meta-analysis. So what's the conclusions? Basically, if you ignore confidence intervals and focus on p less than 0.05, you lose the ability to sensibly summarize evidence across studies. Some people use an example with just 2 different odds ratios. If both find odds ratio of 1.5, but only one has p less than 0.05, some people say they're incompatible, which could follow logically if you say p less than 0.05, p greater than 0.05 means no difference, like an odds ratio of 1, which is different to an odds ratio of 1.5. But presumably the audience to this talk realizes that's wrong, and that's a false argument. To me, this does illustrate why it's bad practice to say p greater than 0.05, no difference. Because if you can't sensibly summarize results across studies, then I think that indicates there's a problem. Cochrane explicitly warns against that. Systematic reviews take an awful lot of time, energy, and effort, and yet at the last hurdle, lots of people, about half the studies, are relying on vote counting of p less than 0.05 for at least some of the outcomes, according to a survey in the Journal of Clinical Epi. It is a bit of a waste of all that effort. Cochrane is okay with vote counting direction of the odds ratios, although it's very weak. The meta-analysis is effectively using the confidence intervals, or you could say use the log odds ratio and the standard error, which is the same information as in the confidence intervals. And so that's a very robust, useful way of combining evidence, as I guess people realise. So this justifies why focus on confidence intervals is really valuable. So why then do people focus on p less than 0.05 if it's known to be a problem? Well, the p-value statement, Wasserstein's 2016 p-value statement, well, we teach it because it's done. That's what researchers and journals use, and we use it because that's what's taught. So if we want to change that practice, then starting with better stats education is one way to start. Another reason people might focus on this is because it's really, really simple to divide results according to p less than 0.05. Really simple rule, anyone can do it. And maybe if you don't really understand stats, you can rely on that rule. Stats courses have a reputation for being hard, and some people who've ended up as professor of statistics have acknowledged to me that they only gradually understood p-values and confidence intervals over the first few years of their careers. They did well in their exams, but they didn't pick up the practical relevance of p-values and confidence intervals from their courses. I'm sure some of you teach in different ways. Some students do obviously get that, but not everybody. Maybe there's a terminology issue. Significance implies important. Non-significance implies irrelevant. Okay, I'm a statistician. I know it means p less than 0.05. I know that isn't the same as important, but my instant reaction to that word is that it makes it sound like it's important. And there's a theory of quick thinking, your reaction to the word significance, slow thinking, analytical mind. So I can bring in my analytical mind and think, I know what p less than 0.05 means. I can do a critical appraisal, but that's effortful. And I'm convinced I'm sometimes fooled or misled by the word significant because I don't always put in that extra effort and time to properly appraise what p less than 0.05 means and the nature of the evidence. Doesn't matter the fact I've been a statistician for many years. That's still my experience, that the word has got too much of a emotional draw on us. And a lot of other people have suggested we avoid that word as well. P less than 0.05, I've come up with that as one alternative, which at least it avoids that evocative language. Why is stats hard? We might say the mean is 3.8 in group A, 4.3 in group B. There's little evidence for a difference in means between groups. Maybe that's okay. I don't know. But I have a bit of an issue with the fact that 3.8 and 4.3 are different. And then we're saying there's not much evidence for a difference in mean. And I think that's potentially a bit confusing. So I prefer study participants' mean is 3.8 in group A, 4.3 in group B. There's little evidence for a difference in population mean between groups, assuming random sampling of participants from the population. So I'm clarifying when we're talking about participants and when we're talking about population. And of course, because it's medical research, observations are usually study participants, not absolutely always. So you could use some other relevant language when they're not. Population. Why do we introduce it? We obviously need to tell the students this, as I'm sure you do. Maybe it's worth telling them quite often. It's a tool to acknowledge focus is not specifically on the participants that we happen to recruit, but we want results that are relevant more generally than that. Random sampling assumption. You can't really understand p-values unless you realize that they're dependent on the assumption of random sampling, and that's what enables the calculations. Population, there's evidence the population is misunderstood. People don't always know what we mean when we say population. It's an everyday word, but the way we use it within inference is obviously different to its everyday meaning. And I've got a colleague who did surveys of what clinicians knew. Quite a few new confidence intervals reflected uncertainty, but they had no idea where the uncertainty came from or why it wasn't just a single calculated value. We assume random sampling so we can do the calculations, but usually in medical research, it's implausible. So the pragmatic reality, we want to assume participants are representative of the population of interest. Distribution of key characteristics is similar in participants and in the population. If they're not entirely representative, we might have bias, bias in selection, bias in measurement, and that's not reflected in this confidence interval, but we might discuss it in discussion sections of articles. We don't want students to lose confidence in confidence intervals. We want them, so I'd like to emphasize good study design minimizes bias. So they don't think, oh, everything's going to be so biased, what's the point? It's our responsibility to design studies well so that confidence intervals are good enough and they're not very biased. I don't know if this is a subtle point, but the study participants are a clearly defined group. The population they were selected at random from is usually an abstract concept because usually we can't actually do random sampling. And yet, when we're referring to the odds ratio in participants, we often call it the best estimate of the odds ratio or the odds ratio in the sample. Estimate of the population, sample of the population. Participants are a clearly defined group. Population they were selected at random from is an abstract concept. So it's a more challenging concept. So I prefer to say odds ratio and study participants. And my view is that that clear starting point makes p-values and confidence intervals just that bit easier to understand in contrast with a very clear, transparent starting point. How are we going to interpret p-values? Well, avoid dichotomizing according to p less than 0.05. Significant or not is bad, and the word significant has got too much of an emotional pull. Reject or don't reject the null hypothesis doesn't have the same emotional pull, but is still dichotomizing. So we could say strength of evidence to reject the null hypothesis, strength of evidence in favor of association in the population. The ASA p-value statement 2016 encourages level of compatibility, that it encourages use of the word compatibility. And then I like to use it in a slightly different way, compatibility with random selection of participants from a population where this association doesn't exist. So I'm giving the assumption of random sampling and I'm giving the relationship between participants and the population so that I'm reminding people who the population is. And we can similarly put that into the p-value definition. Probability of getting an association at least this large, assuming participants are randomly selected from a population without any such association. I think people often get students to interpret p-values in a lot of different settings as a tool to help them understand and remind them of what they mean. And so if it's going to be useful for that purpose, then paying attention to the language that we use is worth it, in my view. Confidence intervals. Well, the definition, when we take many repeated random samples from the population and calculate confidence intervals on each, then in the long run, 95% of these confidence intervals will contain the population mean. Simulation exercises are really valuable, as I'm sure you're aware, for teaching the basic principles of statistics. And so we can show this shows the horizontal red line is a fixed population mean. The vertical purple lines represent confidence intervals, which are random intervals because they're based on random samples of the data. And so we can illustrate it like this, and it's useful for students to see different random samples and what they look like, and to see how the theory builds up from that, and the definition usefully interlinks with it. Maybe when you're using it separately from the simulation exercises, it does feel cumbersome, it might be a little bit tricky. A lot of people fall into much simpler phrases instead, informal interpretations. I also find it curious that to me, the definition feels like a property of confidence intervals that everybody should know. It doesn't so much feel like a definition, in my view. If you're being really pedantic and really strict to the frequentist approach, then you can say it's a property of the procedure that generates confidence intervals, and you can't really properly interpret one individual confidence interval. But I guess when we're teaching, few people stick to that very rigid idea, which maybe I don't know if everybody agrees that's technically how it is. So a lot of people might say we're 95% confident that population mean lies within these values. Much more informal, might informally imply a probability distribution on the population parameter, but I don't know, usually people think it's fine. It looks simple, but is it? If people don't understand the population, maybe the tricky bit to understand is a population and why we introduce the concept, and that doesn't help them with that. So if we want to repeatedly define confidence intervals or interpret them so students understand them better, then maybe we shouldn't ignore the tricky bit, which is who is the population anyway? So I've used this successfully with my students, starting with a clear statement, the mean in study participants, and then when we generalise beyond study participants to the population they were selected at random from, we're 95% confident population mean lies, da, da, da. And so it gives a random sampling assumption, it gives a relationship between the participants and the population, and gives the purpose of confidence intervals as being to generalise. Maybe you're comfortable with the word generalize there, maybe you're not. If you're not, you could talk about uncertainty. Uncertainty itself to me is really vague, but if you say uncertainty in population estimate reflecting assumed random choices in selection of participants from the population, then to me that's pretty good and precise and clear. Or we can use precision or imprecision. So to me, what word you use doesn't matter too much, but I feel it's useful to give the assumption of random sampling, participants selected at random from the population, which helps them understand the word population as well. And these are obviously short enough that they can be taught routinely throughout teaching courses. Either stick to the same one, which I tended to start with. I think I had two slightly different versions, but then later on I changed the wording a bit. Of course, they sometimes like the reassurance that they know the wording and can get it correct, but then changing around the wording can be useful to keep them on their toes. And of course, they might describe them in their own words as well. Those all are a little bit Bayesian, you could say, although very well accepted. I think it's slightly truer to the frequentist approach to talk about compatibility. And of course, so the 2016 p-value statement encourages the use of the word compatibility for p-values. By analogy, they work also for confidence intervals. Slightly more cumbersome, perhaps, to use compatibility, but you can. The data is compatible with population means between 5.7 and 5.5 and 5.7, so we can use it. I did write a publication saying it was a good idea. I haven't entirely switched to using it in practice. I guess different people can make their own choices as to what they feel is the best. But there's times I find it really valuable. If a student says there's a 95% probability population mean lies in this interval, you might say, no. I used to respond to this really badly and just say, no. I'd be so confused. And it's better, I'm certain it's better to say no, because you're not allowed to put a probability distribution on a population parameter. That's certainly better than my sort of blank, oh no, you're not allowed. I don't entirely like to rely only on rule calling. So if you want a different way to explain, you can go a bit Bayesian. So to find a probability interval, we need to combine information on compatibility of data with values for population mean with prior information on what values for population mean are plausible. And so the confidence interval gives the compatibility information, but it doesn't give the full, it doesn't have enough information to claim 95% probability. So I like that wording because I can very succinctly explain what extra we need to be able to claim 95% probability. I feel quite strongly now that if somebody is saying we're 95% probable the population mean is in this interval, I know I've confused them so much by saying it's wrong, and I kind of feel we ought to encourage them. They are on the right track. That's at least a crude level of understanding. It's a reasonable approximation in my view, but we may then need to say, well, actually, you won't get marks in exams, and you need to have a slightly different wording, a bit more. There is scope for more nuanced understanding. But given so many people ignore confidence intervals in the literature, we don't want them to think, oh, confidence intervals are too hard for me to understand. So if it's a useful step towards understanding, then why not encourage them? And it's better than thinking 95% of observations are within the confidence interval. Much better. It's useful for students to know the link between confidence intervals and p less than 0.05. But given there's a bit of an issue of people focusing too much and interpreting confidence intervals sometimes according to whether p is less than 0.05, if you want to discourage that, don't give marks for that in the exam. And instead, if they're asked to interpret a confidence interval, then make sure they're clinically interpreting both ends of the confidence interval. Or at least using some language for confidence intervals. I do feel it's good practice that they should clinically interpret both ends. I haven't always done that in my own teaching, but at least using some interpretation of confidence intervals that focuses on the imprecision or however you describe it, not on the p less than 0.05. Language alone is obviously not enough. We need practical examples. So focusing on clinically interpreting confidence intervals is valuable. It's quite handy to look at confidence intervals from well-conducted randomized controlled trials where they can make conclusions like further research needed because the confidence interval is really, really wide, or definitely clinically effective with a fairly narrow confidence interval, or whatever, a range of different interpretations they can make. So in general, I like it if people I like to clarify when I'm referring to participants and when I'm referring to the population, and keep on giving the assumption of random sampling and the relationship between participants and the population. So for a confidence interval, mean is 3.4. The study participants mean is 3.4. With 95% confident population mean is between 3.2 and 3.6, assuming participants are representative of the population. So here I've changed it a little bit to be more pragmatic. So you can, if you want, go to the pragmatic reality that representativeness is usually as good as it gets. Something on distributions. The distributions, they're obviously very valuable steps. If you want to teach distribution-based calculations, then diagrams like this are really valuable, and you can show the limits to calculate 95% confidence intervals on the Z distribution or on T distributions or other distributions. And that is obviously valuable for teaching calculations. But maybe we need to be aware that this looks like 95% coverage. And maybe even if we're not paying attention, we might think it shows 95% coverage of the observations themselves rather than of the sampling distribution. Oh, so there's a fair bit of evidence, certainly my own personal experience and some publications. Some people think 95% of observations lie within the confidence interval, and that's one possible place it could come from. So I've taken to labeling these distributions as artificial. Use of that term alone confused students, but when I explained why I used it, there isn't a study design where we take many repeated random samples. And so the distribution of many repeated random samples of size 20 exists only within computer simulations. And so this distribution isn't the distribution of anything real, it's the distribution of many, many random samples of the same size, which is quite artificial, compared to the distribution of blood pressure of everybody on this talk, where the variability in blood pressure or the distribution represents variability in a group of real people. So it's much more concrete. So that seemed to help when I described why I called it artificial. We can also offset the visual impression of 95% coverage. We can simply draw confidence intervals onto histograms of the data, confidence intervals for the mean. And when I describe confidence intervals as reflecting precision of estimate of population mean based on assumed random choices, then students seem to get bigger sample size, more precision, narrower confidence intervals. And we can show that visually, and they seem to grasp that relationship. And if you want them to calculate confidence intervals, then I've got them to calculate it based on some of the images that they see. So it all triangulates and fits together. Student engagement with concepts is obviously useful. So you can then say which might be a confidence interval. And if you have 3 lines which are very distinct in length, then it may be useful. I started off with 5, 7 lines, and that was quite confusing. But with a small number of lines, then I think that can be valuable. We might introduce a concept before we name it, for instance. That's one possible strategy. P-values, similarly, these are really valuable diagrams for showing us how we calculate p-values. Very useful, distribution of sampling statistics. And up to a point, they might show the continuous nature of p-values. The further into the tails you go, the smaller the p-value. If you're wanting to show the continuous nature of p-values, I like diagrams such as this. This is the log of 1 minus the p-value, so that we've then got a useful scale where we can show a line meaningfully. And this is the Z statistic, or it could be the T statistic or something else. Z, this is the strength of association in study participants divided by its precision of estimate. So the standard error is precision of estimate using strength of associations in study participants to estimate the population strength of association. So if the strength of association is twice the precision of estimate, we have P maybe just less than 0.05, some evidence against the null hypothesis of no association. If the strength of association is 4 times its precision of estimate, then we have very strong evidence against the null hypothesis of no association. So I've given links between different ranges of p-values and strength of evidence, which is appropriate for main hypotheses, well thought through hypotheses with some supporting evidence, some reason to believe they're plausible, not for highly speculative testing. Maybe it's better to use compatibility wording in line with the 2016 p-value statement, level of compatibility with random selection from population without any such association. And this might more readily combine with you're doing highly speculative testing with 10,000 different genes, and then if you've got a p-value where it's a 1 in 1,000 result, you can see that if you've got 10,000 genes, you sometimes get that by random chance. 10,000 speculative tests. And maybe this wording also more readily combines with what's our prior evidence, what are the supporting evidence, how strong and robust is our study, propensity for bias. So you may be aware of people saying we should do scientific inference rather than statistical inference. Less focus on p-values or the statistics and more focus on the broader picture and other studies, which maybe some of you are teaching. But I guess you're also aware that if you don't have a lot of time and your students are new to statistics, it's not necessarily viable to teach it. I don't know how much time you have on your courses, but it obviously takes time to build up to that level of understanding. I've been blessed with some very good feedback. So that I made stats easy to understand, the learning approach was incredible. These classes became a great support and confidence boost. And I know I've inspired people to do similar things. So I'm blessed with these. I've got a strategy that worked for me in terms of my career, I guess, is getting public recommendations on LinkedIn, which somebody was really pressing me to get. And that worked for me, and I'm very privileged to be the winner of the Outstanding Teacher Award. This paper, it does actually give quite a cumbersome interpretation of a confidence interval, which on reflection, it got a bit longer with the reviewing process, and it's a bit long to be used in practice. I justify all the different elements within it, but I think if you're trying to get conceptual understanding, the version here is a bit long, and in fact, Vicky Ryan was inspired by that, but she also used a simplified version in her own teaching. The other things in there I think are good. Some of the things I've been talking about here are in there in that paper. So, in summary, I think it's really good when we teach to remember what major misconceptions students might fall into and the issues of poor standards in the literature and make a conscious effort to steer away from them. So I like to clarify when we're referring to the population and when I'm referring to participants. Refer to the assumption of random sampling from the population routinely in p-value and confidence interval interpretations, and at least sometimes explain the reason for introducing the population concept, not just once at the beginning of the course, but at least once every session you teach, maybe more often, because quite a few, I keep on defining the population and the random sampling assumption pretty much whenever I interpret p-values and confidence intervals. If you're looking at distributions of sampling statistics, and it has seemed to help calling them artificial and explaining why I'm using that term. And then for images, we can engage students with histograms of the data, describing ranges for population mean that are compatible with the data. And so that's a confidence interval. And the p-value, the graph I suggest, gives some idea of the continuous nature of them. So thank you very much for listening. These are the two key publications that I've been that give these ideas, these teaching ideas. So thank you very much. Thank you for listening.
Thank you so much, Hilary. This was an awesome presentation, very insightful for understanding p-values and confidence intervals. And as just a quick reminder to the audience, the session has been recorded and will be available soon on our website and YouTube channel. So if you're not a member, please sign up and join today. But let's go ahead and open up the session for some questions and answers.
Okay. Can't see any questions at the moment.
So Hilary, I'll ask you a quick question. So, the focus here is on teaching students, right? But I often wonder as you're reading papers in the literature, like how often do you see misinterpretations in the literature, right? Like, even if it's not obvious, but sort of like, unobvious misconceptions or the way confidence intervals are stated.
Um, Maybe ignoring confidence intervals is the main one.
Mhm.
Or saying things are incompatible when they clearly aren't paying any attention to the confidence intervals and maybe not the odds ratios themselves either. Yeah, that's an issue. I mean, I guess it's a challenge that I did insist. One time I insisted somebody wasn't uh, um, allowed to say significance in their paper. And then another person was doing a trial and they were being very clear, very honest about all the limitations of it. And they did so well to get a result. And so I actually was thinking, well, it's sad. I found it a bit sad. People would then say, oh, I don't know if I believe you, because they were reading the fact that they were honest and saying that there could be some possible issues and were just reporting that back. And I don't know, I felt they'd done so well to get a P less than 0.05. I wasn't going to say don't use the word significance because I backed them and I liked what they were doing. Although, that's not ideal from a stats perspective, but still. But it's difficult. I mean, it's very difficult to always be. I think to just make sure we never say no difference because P is greater than 0.05 is a bit of a challenge to make sure we never
Right.
do that. In my view,
And
maybe some people have paid more attention for longer and it's no longer a challenge to them.
And there's a couple of questions in the Q&A. There was one on, do you have any thoughts on how to talk about standard errors? Students often wonder what's the difference between standard error and standard deviation.
Um, well, so I guess when I was saying artificial distribution and real distribution, then I think actually the first time that came up was when people were confused about the difference between standard error and standard deviation. So we can say standard error reflects the precision of population estimate when using the participants' mean to estimate the population mean based on assumed random sampling.
Awesome. And let's
Maybe
see,
it's useful. Yeah, maybe it's useful to say the difference between participants' mean and the population mean is on average one standard error. Average, well, so I'm qualifying exactly what average means there.
right. Now let's see, Amy asked, we almost always use the mean when we explain confidence intervals. Students have a difficulty understanding the concept that applies to any statistics. So do you have any tips to further clarify this to students? So confidence intervals for something besides just the mean.
Um, I don't know, well, you can use this same sort of form of wording for difference in mean and lots of different things. I'm not quite sure apart from that. The concept of variability, you can say if you do the study again, you get a different answer. If you do it again, you get a different answer. And each time you get a different answer because each time you're selecting different samples of participants. And so the confidence interval is a way of saying how similar or how different are your answers likely to be.
Yeah, actually, I think that's a great way to say it, and that wouldn't matter what the statistic is. Let's see, Mark Robinson said, thank you for a great talk. If you were a journal editor, what would be your instructions to authors for reporting statistical results, including effect sizes, p-values, and significance thresholds? That might be a
Um,
whole other talk. It's a great question.
I'm not sure that I like significance thresholds very much. I just like gradations of evidence or paying attention to the confidence interval. Certainly, if you've got huge sample size and everything's got p less than 0.05, I just say, well, look at the effect size. Is it big enough to matter? No, I wonder with p-values, there are rules as to what you can say, which people may or may not agree with rules, but then maybe they're better than not having rules because otherwise people might say very strong evidence when you've got p 0.04 or something. And I wonder, I think maybe it would be useful if there's rules as to an odds ratio of 1.5 is what would it be, a moderate effect? It does depend rather on the situation.
Yeah, and I would agree on that statement. I tell my students all the time that, I often quote the Cohen book for interpretations of effect sizes and things like that. But, I started out life as a bench scientist and, for calibrating an instrument, I needed an R squared that had like, 5 nines in it to have a significance, calibration for my instrument for the day, So that was like anything less than that was not acceptable in the laboratory world, which would be unheard of in behavioral science. But there was an additional question here on I believe that confidence intervals and p-values are fundamental pillars of statistics and invaluable to researchers. So thank you very much for this discussion. As you mentioned, we rely on artificial sampling distributions for decision making, comparing them with the practical data used in our analyses. I'm quite doubtful, however, about how often this approach truly affects reality.
So in other words, is the concern that the distributions aren't exactly normal, maybe? Admittedly normal. I'm not sure how much of a concern that is with big sample sizes because we have regression to the mean. No, central limit theorem. And often it's more about the distribution of means that may be more of importance. But I guess the more complicated a regression model, if you haven't got that many people in it and you've got lots of predictors, it might become more important. I don't know how important. Then, of course, you can do bootstrap. There are ways you can avoid it. I don't know. I don't necessarily do that so often, but I guess with modern computer power, you could quite easily. Are people using, I don't know if people are using these more often in practice with modern computers. Some of them make the assumption that the sample is the population.
Right.
Maybe
Yeah,
that's not really a
which
problem. I don't know.
that's a whole
It's a,
other like bag of
yeah,
terms.
yeah. The bigger the sample size, then it's probably a pretty reasonable assumption. Maybe with a small one, I'm not an expert on exactly which behaves better in what situations.
Yeah, one person here had a suggestion. It says for absolute beginners, they like to talk about fish, like weights, lengths, species, etc. So rather than starting about talking about human subjects, folks seem to understand that if you go back to the experiment, do it all over again, drop the net into the lake, they'll come up with different fish and encourages the concept of sampling variation. So yeah,
Okay, maybe it makes it more fun. One
I
time I
think
did
so.
some. One time I just had weights of kittens, cats and kittens, and somebody said, "Oh, that was nice." Slightly more playful instead of all this death and disease that we often talk about.
Right. Yeah,
Yeah,
awesome.
well, obviously that works for you, so it sounds a good idea. Yeah, and
Um,
there's the concept of a sampling frame that for random sampling you need a sampling frame, and maybe people can get that a bit more with the net and different fish, and it's more, well, it's not exactly random sampling, I suppose, when you drop the net into the lake, but you might imagine they move around at random. So it does give a bit the sense of the sampling frame in a way, all the fish in the lake.
awesome.
Yeah, it's quite hard, isn't it? There's so much to stats, and it takes
Yeah, I think
practice.
this is great. Thank you so much. It was very helpful.
Okay, thank you very much. Thank you for the opportunity.
Thank you.